in a fluorescent light, the electrons come in and they excite mercury, which gives off UV light, an intense UV light that you can't see and would hurt your eyes and give you cancer if you did. So that's not good. So what we do is coat the inside of the light bulb with a fluorescent material that behaves like this. And the UV light from the mercury inside your fluorescent lamp that's given off jumps you up to here, an energy you can't see. You can't see the color of this photon. And then that fluorescent paint, essentially, that's on the inside of a tube, of a fluorescent light bulb, behaves this way, so it'll absorb that UV light in and it'll give off visible light out. That is fluorescence.
The bright green color on safety vests and cycling jerseys and things like that?
That's just
Does that work?
mostly.
They don't look so obnoxious inside the regular incandescent light. If you take it out in the sunlight, you get blind.
It's more of the intensity of light and the way there's mechanical properties. They're made out of corner reflectors that make sure all the light gets focused back at you if it's coming from your direction. Now, what does happen though in clothing here is color-safe bleach. How can you have color-safe bleach? Bleach is going to take the color out of it, it's going to make it white. So how do I make my clothes look brighter without, how does that work? That's how it works. It's fluorescent dye. They don't tell you that. It's not in the label. But a lot of color-safe bleach is fluorescent dye. It's getting UV light from the sun or from the light bulbs, wherever it is, and it's re-emitting it as visible, kind of a broader spectrum visible white light. And so everything just looks brighter. It looks brighter because your clothing is actually emitting light from this fluorescent dye that's in there. It's taking parts of the spectrum you don't normally see and it's converting it really into visible light through this process of taking the higher energy photons in and giving lower energy photons out. Now, of course, this one will also ultimately come down from this state to this state. I'll get another photon out. So sometimes this is the one you're seeing, sometimes this is the one you're seeing. It depends on what the actual energy levels are there, and they're relative to one another. So that's fluorescence. Now the question becomes phosphorescence. Phosphorescence is the same kind of process, except that there's some reason I'm not allowed to make one of these transitions. I'm barred from doing it. And there's a number of ways that can happen. I don't want to get into details of that. That gets into some more complicated quantum mechanics and some math that I promised I wouldn't go into. But essentially, I can have what's called a prohibited transition. There's a rule somewhere that says this can't happen. I'm not allowed to do that. But in quantum mechanics, there's almost nothing that you're really, really not allowed to do. You're just really not supposed to do. So it takes you a lot longer to do it. The probability of it happening. When I say something doesn't happen, what I mean is the probability is very small. And that's a general physics thing to think about. When we say never, what never means is the probability of something happening is less than once in 10 times the lifetime of the universe. It's never zero. It's just less than 10 times the lifetime of the universe, so you'll never see it. That means never. So when we say prohibited, we don't mean never, can't happen, absolutely no way. What we mean is the probability is fairly small. The flip side of that, the equivalent statement to the probability of a transition being small means that it takes a long time for it to happen. The lifetime is long. So instead of fluorescence, which happens essentially instantly, phosphorescence will take time. It will take seconds, it may take minutes. And that's how glow-in-dark paint works. I'm sitting here and I can take in the light, and the light that I'm taking, these photons, will bring me up to this level. They fall down to here immediately. And then they wait because they're not allowed to get back down to that ground state. And one or two at a time will go after a while. And as they drop down, I'm getting these photons off minutes later. And that's why it's glow in the dark. That's also why glow in the dark stuff is that weird greenish color. Because all you're looking at is this specific transition from here to here. You don't have the full spectrum of light. I have all the light coming in that's charging it up. When you do that, you're pumping all these electrons up the top. And then as they decay, more slowly over time, I have a much dimmer fluorescent light that comes off. That's also why it starts out bright and kind of tapers off. Because the more of them that manage to make this transition, there's fewer left, so the light gets dimmer over time. And a lot of the, coming up with better phosphorescent, better glow-in-the-dark material is just trying to play around with chemistry to figure out how I can get things where this transition is more and more good.
So, two things I just want to check on. You're asking different
spacing and the transitions here.
Okay, and then the other question is this what the glow sticks that kids use now at Halloween?
Glow sticks are,
Or the things used at parties with the, the people put
right,
on
those
the
are, it's a similar process. The difference is that the energy coming in is a chemical energy, not a photon energy. So the chemistry takes care of that.
Yeah, so I understand phosphorescence, but in fluorescence, you're only seeing that difference in the top orbit. Why are you not seeing the transition down from?
It comes out. It's just what color it happens to be. Typically, because these orbitals are not evenly spaced, one of them will be one that's in the visible spectrum. The electromagnetic spectrum, the range of energies a photon can have is enormous. And visible light is a teeny tiny little sliver. So the stuff that we interact with and we think about is really just those, it just happens to be in that tiny little sliver of energies. It's a very, very narrow range of energies that are visible to us. Everything else is, we call it UV and infrared, and those are way, way, way bigger each than the actual visible spectrum is. So, but the answer is that they do all come out. Now, the one last thing I want to get to before we move on to nuclear physics is lasers. I'll see what a laser is, and that will be atomic physics. So, laser is it's a tube where I have two mirrors, here and here. And so the photons can bounce back and forth between the two mirrors. And what I have around the outside of the laser somehow, there's different ways to make it, but I have something that's going to add energy in there. So I have energy coming in somehow here. I have my atoms that are floating around in there. It can be a crystal, it can be a gas, it can be all kinds of things. Some kind of atom where I have these transitions that are allowed. And as this energy comes in, I'm pushing the electrons up, and they're coming back down, and they're emitting photons of this particular size. So all this energy is coming in. I have all the atoms here, and now I have photons that are also flying around back and forth, kind of going all over the place. These photons are the same energy. They just came out, the same transition energy. So when a photon comes in, I have that pushing the electrons here again to a higher orbit. So I have this constant process where all the electrons are going up. The electrons are making this transition. They all start out here. I start pumping energy in. The photons move up. They fall back down. They spit out a photon. They move up again. If they get hit by a photon. But I'm adding energy all the time as this is happening. So I keep pumping these photons up into the electrons up into the higher state. So there's photons flying around all over the place. But everything else is also being moved up to a higher orbital and falling back down. So because I keep adding more and more energy from outside, whatever's outside the laser, whenever I plug the laser into the wall, I end up in a place where most of my atoms have the electrons that are up in this higher orbital. And I have a lot of these photons flying around. Now there's a special thing that happens. And so these photons are flying around and they're trapped in here between these two mirrors. So they're going back and forth and back and forth. And there keep being more and more and more of them because I keep adding more energy to this. If I just added the energy from outside, and I had these transitions, I didn't have the mirror, that's what we were talking about with the fluorescent light or with the sodium vapor light. That's basically that process. What happens in a laser is it's not just the energy that comes into here that's doing it, but it's the photons themselves, because they're trapped in these mirrors, that are also making these transitions happen. And the special thing that happens with the photons is that when a photon comes in and forces this transition, and the photon comes back out again, the two photons are marching in lockstep. They're together. Normally, the light is just coming out any which way. All my photon waves are just coming this way and that way and like this, just kind of all over the place. It's a big mess. That's regular light. In a laser, what happens, because I have the photon come in the atom, comes out with new photon. Go back one. I have an atom with the electron in the second state because of this energy. It's sitting there. My photon comes in, and now I have that photon causes the electron to go down. because this has too much energy. It's kind of a trigger, it kicks it, and now we have two photons come out. These two photons will march in lockstep. Their waves will be exactly synchronized. This happens again and again and again between these two mirrors. So what I end up with, is a whole bunch of light, all these photons, that if I now put a hole in one of these mirrors, or I make one 80% reflective, so some light can get through, what comes out the end here are a whole bunch of photons that are exactly in lockstep. That's what a laser is. So they're much more focused, they're together, and there's a lot of things I can do now that I have all my photons in lockstep.
I thought you said that if you add the photon, when the electron is already in the second orbit, it could move it into the third orbit. So why does this now cause that electron to go back to the first orbit?
It could if it happens to be the right wavelength. The reason it does that is that the photon that comes in, because it came from the same kind of atom, transitioning the same kind of orbits, is exactly the amount of energy that spacing is between the first and second orbit. So my photon coming in is exactly this size. It's exactly this size. So it forces this transition because it's coupled to that. If I'm in this state and a photon comes in, it's not going to match up with any of these other transitions. So it won't want to kick it up. It'll trigger it to come down because it matches that transition exactly.
When we give lectures with the lasers and we have in our hands, it's
Yes.
a similar process?
This is exactly it. This is what it is. And because these are in lockstep like that, that's why you can have a single focused beam that comes out. It's also why it has that kind of speckly look. Barbara?
I'm a little confused as to why, if the amount of energy in that photon is just the exact amount of that spacing,
Right.
why would it kick it down? Why wouldn't it just maintain it at that upper level?
It could just kind of, well, because when things match, there's a coupling between them. They communicate essentially with each other. And it's just a trigger that makes it happen. It's not, there's no intuitive process that goes along with it other than to think, well, if we're almost exactly the same, if the same amount of energy, I'm going to trigger a process that we would have done anyway, it just makes it happen faster. It just acts as a trigger because it happens to match.
Is it kind of like the photon sort of replaces the electron? Like allows the electron to come down because the photon came in?
Intuitively, you can think of it that way. Yeah, the real reason is mathematical, but we always have to have kind of intuitive understandings of these, and that will give you a basic idea.
Does this only work with certain materials that have certain energy steps, which is why you get lasers in certain different colors?
It's easier to do with certain materials. It's just, you can make the material more easily, it holds together, but it would work with essentially anything.
Just the energy that goes to the atom will provoke the electron to move from one orbit to the outside orbit.
Right.
And other times it will just bounce energy and decrease the energy in decay, meaning the electron will move to a closer to the nucleus. What does it make that sometimes the energy will cause it to go to an outside orbit or go into a closer orbit to the nucleus?
If I add energy and the energy is absorbed, the thing will go to an but if I'm in an outer orbit and I already want to get down and I need an excuse to do it, sometimes I can take that as my excuse.
So is it the wavelength of the photon that determines whether that electron will move in either direction?
If the wavelength, well, the electron is always going to go down at some point. But if I happen to have a photon with just the right wavelength, it'll trigger it to happen more quickly. If I have a photon of that wavelength though, and I'm already here, and it matches this, if it doesn't match any of the other transitions, it's not going to make it. So it's really what matches up with what that makes the difference. Okay.
So, Josh, just really fast, so in a practical application, just to help my brain wrap around it, with something like when laser is used to like remove hair from someplace on the body.
Right.
It's this process?
It's this process.
It's this process.
It's because all those photons
So
are
the beam is
together.
what causes the hair to like...
It's the heat that the beam generates. But the reason I can get a spot with so much heat is because I've got all my photons lined up. Right? Jane?
How come one photon produces the two photons coming out?
Because I've added that energy from outside that put the electron in the higher orbital, so it's waiting to go down. I'm an atom, it's kind of pregnant, and I'm waiting to release this energy, and the photon coming in that happens to match the energy I'm going to release triggers me to do that. It encourages me to do it, so then there's the one that came in, and then there's mine. That's why there's two. Okay, one last one.
There are three processes here. One is the generation of the frequency of the laser
Right.
frequency, the amplification. Now, the amplification of it is done by the mirrors, right?
The amplification is because I'm adding the energy to pump these atoms up into the higher orbitals, so they can get pregnant.
And what about the phase, the coherence?
The coherence comes from the fact that I have the photon coming in that triggers the other photon to go out. It's not naturally decaying, it's triggered by that photon coming in. That's where the coherence comes from. The coherence is the real word for the waves being lined up together. Okay, I'm going to go ahead here to get to a little bit of nuclear physics here before we're done today. So nuclear physics is in some ways, there's some of the same concepts. We still have the shells, we still have energy levels. This picture won't look anything like this, but this picture looks pretty much the same. But we know a lot less. So the nucleus is made up of neutrons and protons. We talked a little bit about those last week. The protons have a positive charge, the neutron has no charge. This is electric charge. They're about the same mass. And they have things inside them, they have size. So I have protons, neutrons. They kind of come together in a ball. And what I'm going to be describing today is called the toy model of nuclear structure, nuclear physics. This is the Bohr atom. We said the Bohr atom is not, it helps us think about it. We can solve all these problems. We can design lasers. We can have all kinds of modern technology. But it's not, but it really looks like this, right? It doesn't really look like those rings. In the same way, when we get to talking about nuclear physics, we're talking about the toy model. We draw it as these balls that are all kind of together in a bigger ball, and that's not what's really going on. There's really a similar kind of smearing as with the electrons in the nucleus. It's a little more complicated and a little less relevant to really anything that goes on within what we talk about in nuclear physics. So I have this ball, and it has these different numbers of protons and neutrons in it. Now, the protons are positively charged. So instead of P, I can put plus, plus. And what we know about two positively charged things, if they're near each other, they want to push apart. Plus and minus wants to come together. Plus and plus, or minus and minus, want to push apart. So I have this electromagnetic force that's pushing these two protons apart. They don't want to be near each other. So how do they stick together? They stick together from something called the strong nuclear force. The strong nuclear force is very, 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 very strong and very, very short-ranged. The electromagnetic force, these positive charges here, are pushing apart. It's much, much weaker, but it goes over infinite range. And it's what determines essentially everything that happens in the nucleus is because of the balancing of those two forces. A very strong short-range force and a weaker long-range force. The first way we see this happening is that if I have the simplest atom I can have, the simplest nucleus, is one proton. That's just hydrogen. No conflict there, everything's fine. That's what I do right there. That's your hydrogen atom. If I want to have a second proton here, I have a problem. Because I have this question of the balancing of forces. I have a strong force that's pulling them together. I have the electromagnetic force that's pushing them apart. And in this case, because there are only two of these things, I don't have that much strong force because I've only got two of them. If I add a neutron here, the magic thing about the neutron that makes this work is that the neutron does not have a charge, but it does have a strong force. It only feels one of these two. The protons feel both of them. So there's this internal conflict. Do we come together? Do we go apart? I don't know. The neutron only wants to stay together. It does not want to blow anything apart. It does not feel that other force. So what I can do is balance out. If I keep adding neutrons, I can make protons that would have wanted to fly apart. I can increase the score on the strong force side without impacting the score on the repulsion side, on the electromagnetic side. And I can get things to stick together if I add neutrons. That's why a nucleus has to have protons and neutrons to be a nucleus, otherwise it will all fall apart.
And if this is moving fast where you intend to be in front of it, getting answer finally, are buckyballs the next step in this process?
No, those are, it's
Or
a
is that
separate,
something
that's chemistry.
That's fine, thank you. Just
So,
wanted to be sure.
way up on the top of the chart.
Okay, just wanted
So what we have is a number of these things together. And so the one thing I have to make sure we understand before we go on too far here is that different atoms, there's different kinds of different atoms I can have. And what makes one atom different from another atom, different nucleus, it's the number of protons and neutrons in the nucleus. I can make different nuclei just by changing how many things are in here, and if I change what's in the nucleus, that changes what kind of atom it is. If I change the number of protons, which changes the total charge of the nucleus, the total charge here, then I'm changing what element it is, whether it's gold or iron or any of the basic elements, lead, anything. If I change the number of neutrons, it's the same element, it's the same kind of atom. It's still lead, it's still gold, it's still uranium. But it has a different number of neutrons, we call that a different isotope. So a different isotope is like different flavors of the same kind of atom. That changes the way it behaves a little bit. It doesn't change anything with the electrons. It doesn't change anything about the way the atom itself behaves, but it changes the way that the nucleus will behave, depending on what that balance is. So now that I have this idea here, I'll come back to that, that I can have different numbers of neutrons and different numbers of protons. That's called the neutron number and the proton number. I can see what kinds of atoms can I make. Just how many protons can I put in here before the thing falls apart, or before I need to add another neutron to keep it together. With just two, it'll fall apart. With two protons and a neutron, it falls apart. If I add one neutron there, then the strong force starts winning, and it can stay together again. If I add another proton, then the electromagnetic force starts winning. So I have to balance these two forces, pushing it apart and pulling it together, and I have to see what happens, which one wins. And if the strong force wins, that is, if the strong force clearly wins, that is a stable atom. That's your everyday matter. If the balance is all the way on the side of the electromagnetic force, I have too many protons, not enough neutrons, the thing flies apart. It never forms in the first place. It's not a thing. Right? I can't make a nucleus that way. If I'm right on the edge and the two forces are fighting each other, that is an unstable atom. That's where when we think of radioactivity, most radioactivity, that's what you're talking about. You're talking about an atom that has this tug of war between the attraction and repulsion, and sooner or later, the repulsion wins, and the thing falls apart. There's different ways it can fall apart. Sometimes it falls apart if it's got too many protons. Maybe just one of these just flies off, and now I'm okay. If I'm not okay like this, I'm okay like this, I can just eject one. Sometimes I'll take two protons and a neutron, which is the helium nucleus, or two protons and two neutrons. We'll say two protons and a neutron, and just so this part will come off. That's another kind of radioactivity that's called alpha decay. I can also convert a neutron into a proton and an electron by having the neutron itself decay, and then I have an electron come off. Or I can have, well, call it that way, that's beta decay. Beta is an electron. It's another word for electron. So I have, alpha, gamma, and beta, which is just a helium nucleus, like this, a photon, or an electron that can come off. Different ways this can break up. The other thing that can happen is the entire thing can fracture down the middle, and it can split into two pieces. That's nuclear fission. So the way to understand this, to look at it first, I have a few of these pictures that are fairly similar, that show different things, so I'll run through quickly, is by plotting the nuclear landscape. So what I have here is, this is how many neutrons I have. As I go this way, I'm adding more and more neutrons. I just keep adding ends in the little nucleus. And if I go this way, I add more and more protons. So right down here, I've got two neutrons, two protons, that puts me right there. That's helium. As I go up this way, these are all the different elements. And as I go this way, these are the different isotopes of the same element, if I stay in the same place. So there's certain allowed numbers I can have. Like I said, I can have two protons and a neutron, that's okay. Two protons and no neutrons is not okay. So the okay things, the things that are stable, the cases where the strong force holding it together clearly wins, those are the stable nuclei, and that's what's plotted in black here. And so there's a few hundred of those that are there that we know about. Then I have areas where there's that tug of war going on. Maybe it's stable, maybe it's not stable. It's going to fall apart at some point, the radioactive. And that's the areas around here. So these are all known. All this yellow stuff is atoms that are known, nuclei that are known, but they're unstable. And then what this line is at the top, all of a sudden it turns white. There's nothing there. That means the electromagnetic force, the repulsive force between the protons, is so strong that it completely overwhelms the strong nuclear force, and the thing falls apart completely. Or you can't make anything up there. Because if I add another plus to it, it won't stay. It'll fall apart. This is actually called at the top there, it's a solid line. That's called the drip line. Because if I'm right at the point where it balances, where those two forces, the repulsion force and the attractive force, are exactly balanced, and I take one proton and I pull it up, it doesn't stick, it just kind of falls off, like drips off the edge. And that's the drip line. And I can calculate very easily exactly where that drip line is. We can measure where that is. We know what's stable, we know what's not stable, so that's easy to do. So that's a very well-defined line. This is where I have too many protons to have a stable nucleus. On this side, it's different. This is where I have too many neutrons to make a stable nucleus. Now remember, it's the protons that are pushing apart. The neutrons are helping you stay together. So how do I have a case where the neutrons are making me unstable? It turns out we don't know how the strong nuclear force works outside of a neutron or a proton. We know very well how it works inside to hold the neutron itself together. We'll talk about that in a week. But we don't really understand this force. We don't understand what happens when I get 20 or 30 or 50 of these things in a ball, what all those forces are. What happens is that the neutrons, I can't just have a ball of neutrons. That won't be stable. That'll fall apart. I need to have protons in there as well. I need to have those two different flavors for the strong force to really work. But unlike the case where I have the electromagnetic repulsion between the two positive protons pushing them apart, there's nothing really pushing them apart. It just doesn't stick together. And because we don't understand that, that's labeled on all these kinds of charts, terra incognita. We don't know where that is, and we can't really explore it because we don't know how to make anything out here. We can have accelerators, we can have reactors, we can make all kinds of crazy things, but there's just no way that we have to make all this stuff out here. The only thing that comes close, if I go all pure neutrons, I have all my neutrons together, that might remind you of something like a neutron star, which is again more astronomy than I'm not going to get into. That's where it's just a ball of pure neutrons, and there's so many there that gravity takes over. That's the one case where gravity actually makes a difference, and the gravity is able to keep all the neutrons together, and it becomes stable way out here in the corner. But for the most part, I've got this stability here. This is called the valley of stability. Sometimes how much it sticks together is drawn as hills, so this becomes the valley. And then this thing up here is the island of stability, which when I was in grad school was drawn as the island of stability question mark. And now it is the island of stability, which is what happens when you're in school for a while. That has been, this is now the same plot. Again, I have the number of protons up here, the number of neutrons up here, and now what the colors correspond to how long the thing lives. So the stuff that's black in the middle, these are the things that are stable. What stable means, again, it won't fall apart. What it really means is more than 1 million years. The lifetime is more than 1 million years. Then as I get further and further away from here, the different colors means it lives shorter and shorter times. Until I come up here right along the proton drip line, which is where the protons don't stick anymore, and I have less than 1/10 of a second. So these are the half-lives, which is, you can think of it as how radioactive something is, how likely it is to split apart. And these are all measured things. So we make these things in reactors, we make them in accelerators, we measure how long it takes them to fall apart, and then you can plot this nice graph. Okay?
Why wouldn't, if you just have neutrons, the thing just collapse into itself?
There's nothing that makes it collapse. There's nothing pulling it together. The strong force between the neutrons and the protons, or the neutrons and the neutrons, is it makes them stick, but it doesn't. It's not like gravity. It's not pulling them into each other. It's just keeping them together in a ball.
I see, okay.
And there are the strong force inside the neutrons and protons. Something we'll talk about later, and that gets more interesting. The way to think of it is that these things are emitting glue. There's these gluon particles, and the glue is kind of the shaggy edges around it. and it's sticky like glue. So